Hi everyone. Today we are going to be going over 11.5. Fun fact, I'm really frustrated right now. I'm recording this video for the third time. The first time I'm doing it, my Apple Pencil ran out of battery 30 minutes into the video, so I have to redo it. The second time I'm doing it, I forgot to turn on the microphone, so this is the third time, and hopefully this time is better. And I checked the microphone, I checked out my Apple Pencil, so everything should be okay now. Okay, so we were talking about how to test sequence and series, right? 11.3, we have integral test. Okay, 11.4, we want comparison test. And the limit comparison test. Well, everything is working okay, but we do have some restrictions. For integral test, we require it's positive, continuous, and decreasing. For comparison test, we do require it to be positive. Of course, in general, when you sum a lot of terms together, it's very possible you will have negative terms in your series. So now we are going to try to handle the series with negative terms in it. We first start by doing something called the alternating series test. Okay, so let's define what do you mean by alternating series. Alternating means we have a series. It has positive and negative terms, and these positive and negative terms exactly alternate each other one after another. So we will either have positive, negative, positive, negative, positive, negative, and keep going forever, or we will have negative, positive, negative, positive, and going forever. We will never have plus plus or minus minus together. It's going to be one positive and one negative. For example, we can have something like this. 7 and 8. From here you can see, it's very easy to see this is nothing but a series we had before, which is 1 over n, which is the harmonic series. But instead of taking all the terms to be positive, we do require some of them to be negative, and they have to be exactly one positive, one negative, one positive, one negative, one positive, one negative, and go on. This is called alternating series. This will be what we'll be handling for this whole section. Now, how do we write down the formula? How do we write down the formula of something like this? Well, of course, we want to have sum n from 1 to infinity, an. We need to give a formula for this an, right? Now, what is the formula of this an? For our case, it's fairly easy. It's 1 over n. The only difference is we want to tell people sometimes we should take positive, sometimes we should take negative. So a natural way to write down is we have a piecewise formula. Sometimes it's positive 1 over n, like 1, 1/3, 1/5. Sometimes it's negative. It depends on if n is odd, it's positive, number 1, number 3, number 5, and if n is even. Okay, so we can certainly write down something like this, which will work. Now what we want to do is we want to use some useful mathematical trick to make the formula simpler. If you think about it, you go from positive to negative, and then you go from negative to positive. It's almost like you're timing -1 at every time, which would basically do the same job, right? This is not the only way to do the job, but this definitely does get the job done. And if you recall, if we time a number, okay, the same number every time, for example, times 1/3, times 1/3, times 1/3, we have a name for this. This is called geometric. And r basically equals -1 if you just talk about the sign. Then a natural way is try to borrow from the formula of the geometric series, which just give you -1 and -1. This means every time you increase your n, you times another -1. You times -1 for multiple times. Okay? This will handle the sign. Then what we can do is we can simply, for this series here, we first write down the value 1 over n. Then we do -1. This will handle the plus and minus. Okay, putting these two parts together, we have the alternating series. If you don't believe it, let's plug in some number. N equals 1. which is 1, n equals to negative 1 to the 2 minus 1, which is negative 1 to the 1, which is nothing but negative 1/2. And you can see if you go another one, it's 3 minus 1, it will give you a plus. And then, of course, you have a 1/3 and 1/3 here. Okay, so several tips to write down. Number 1, when we see an alternating series, we basically see two parts. The first part is going to be a series, which is basically positive, like the 1 over n here. It just takes care of the value. The second part will tell you it's alternating. It's going to be a plus, minus, and the way to tell it is actually times a power of negative 1. Okay. Now keep in mind, for alternating series, we do have two situations. Very small difference. Basically, the first type is we start with the positive. That means the first term is positive, and starting from there, you start to alternate. The second case is the first one is negative. Starting from there, you start to alternate. Okay? Their formula should be very similar. And the only difference is, for this one, you just let n start from 1, you start from positive. And if you wanted to start from negative, you just use negative 1 to the n instead, which means you add another negative 1 to the whole thing, which basically you give you something alternating, which also starts from the very beginning to be negative. Okay, so that's the definition of the alternating series. I write it down in the notes. Like I said, two parts. The first part is going to be a Bn, which tells you how big the series is. Don't worry about the sign, so it's always positive. The second part will be how you tell it's alternating. Basically, we times a negative 1 to a power. And there's a difference between the two things I just underlined. For the first one here, you start with a negative and alternate. For this one here, you start with a positive and you alternate. If this looks confusing to you, just try to write down several examples. You will see. Okay, they definitely get the job done. So that's the first one. Okay, now we know what an alternating series is. The next job is try to see, can we decide if an alternating series is convergent or divergent? To do that, we have a very convenient theorem, which is called the alternating series test. So let's take a look of this alternating series test. So if it's already alternating, like we said, we have only two cases. If it's alternating, ignore the plus minus sign. Just focus on the part which is positive. We need to check two conditions. Number 1, if it's decreasing. Okay. Number 2, if the limit is 0. If we check these two, we found they're all satisfied. Then, according to the alternating series test, we can say the whole series is convergent. Okay, this is what the theorem says. Let's try to write down several examples using the theorem, and then we come back and talk about why these two will be enough. Okay, these two conditions, decreasing and equals 0, when you take the limit, will be enough to say the whole thing is convergent. But for now, let's just try it. Apply it. First example, let's write down this. Okay, number 1, can you recognize it's alternating? Well, the first way to do it is just try several terms. N equals 1, negative 1 to the 1, negative 1 over 1. Okay, negative 1 to the square, positive 1/2, negative 1/3. Okay, you notice, even n is even, negative 1 to the even power. Okay, 4, 6, 8, always give you positive. When n is odd, 1, 3, 5, it always give you negative. So, of course, this is alternating. Another way to simply say is just, I look at this. This looks exactly as the definition, so it's alternating. Good. Now when you see it's alternating, you already know we need to use the alternating test. The first thing you need to verify is what is your Bn. In this case, after you throw away the negative 1 power, you have 1 over n. Now we just need to check the two things required by the theorem. First one, is Bn decreasing? Check yourself, is 1 over n decreasing? piece of cake, right? The bottom keeps increasing. Okay, so the whole thing, after you flip it, it is decreasing. So check. Let me use this. Check. Okay. Number 2. What's the limit? N goes to infinity. Bn. In this case, 1 over n. Clearly it's 0. Okay, so let's check. It's alternating. It's decreasing. And limit is 0. All checked. We can say that is convergent by the alternating series test. Okay, let's say it again. We recognize it's alternating, then we realize we need to use the alternating series test. To do that, we just take out the 1 over n. We say if it's decreasing, and in this case, yes. If it's 0, if you take the limit, in this case, it's yes. Then, automatically by the series test, we can say it is convergent. Very easy, right? Let's try a slightly harder one. Okay. Number 1, is it alternating? Again, we look at the negative 1 to the power. Okay. Even though we actually have n minus 1 here, but now we know it only shifts the first term. Okay, it's just a matter of, do you start alternating from the beginning, or do you start do you start with positive and then alternate, or do you start with negative and then alternate? So given that, we really don't feel weird. We just say it's alternating. Moreover, our Bn is just going to be the part left if we remove the sign. Okay, to apply. Is Bn decreasing? The one before is pretty easy, 1 over n. The bottom keep getting bigger, the top stay the same, so of course the whole thing keep getting smaller. For this one, the top keep getting bigger, the bottom keep getting bigger. It's not so easy to say. So probably you need to show some careful calculation to people that this is decreasing. And we have multiple ways of doing it. I think for this one, we can simply pick, we try to take the derivative, we try to show that it is less than 0. Okay. It doesn't have to be always decreasing, as long as it start to decrease, starting from a certain term, like starting from the third term, it started to decrease. Then the first two really doesn't matter. Okay? With that in mind, let's first define fx to be x over x squared plus 1. And the reason is because you can now take the derivative with n. Now what you can do is you take this, square the bottom, quotient rule, okay, x squared plus 1 minus 2x squared, which is 1 minus x squared. Okay, we want this one to be negative, remember? So the bottom is always positive. Great. The top will be less than 0 as long as x is a little bit bigger than 1. Because when x is 1, this one is going to be 1. 1 minus 1 equals 0. But when x is bigger than 1, x squared will be bigger than 1. The whole thing will be negative. So it's safe for us to say this is less than 0 for x bigger than 1. Therefore, starting from the first or the second term, the sequence is going to be decreasing. We can finally say, check, this is decreasing. To complete the second, limit n goes to infinity Bn. What's the limit of this thing here? Now, leading term, right? It's infinity over infinity. Leading term will give you the answer, or you can use L'Hopital. Either way, this gives you 0, so check. Therefore, sum. Is convergent by the alternating series test. Okay, so personally I think alternating series test is really easy because number one, it's really easy to recognize it is alternating. Number two, once you recognize it's alternating, it's really easy to know what to do next. You just need to show something is decreasing, and you need to show the limit is 0. Both of them are pretty easy, okay? I think that's pretty much it. Now check a little bit about the third example. Let's see what happens if the alternating series fail. Okay. We are familiar with this already, so I'm going to say it quickly. It's alternating. Okay, I want to check number one. Is it decreasing? Well, cosine 1 over n, right? Let me write it down. Bn equals cosine 1 over n. To show this one is decreasing, you can either show by graph or easiest of all, you just take the derivative. Cosine give you a negative sign by the chain rule times the derivative of 1 over x. All of this gives you sine 1 over x divided by x squared. The bottom is positive. Okay. The top is, remember, 1 over x is very close to 0, or at least it's small, when x is just a little bit bigger. Then sine of something small but positive will give you something positive. So together, bigger than 0. So is it decreasing? No. Number 2, what's the limit? We already know 1 over n, when n goes to infinity, is going to be 0. Then the whole thing will be just cosine 0, which is 1. Not 0, so number 2, not satisfied. Okay, from here you can see the alternating series test fail. Let me write it down. Using abbreviations, alternating series test fail. Okay, but then you need to think about another thing, that is, if it fails, what conclusion can you say? The first one is, since I cannot show it's convergent, therefore it must be divergent. Is this the right thing to say? Okay. Think about it. If you cannot show, you cannot get what you want, is it because the thing itself is wrong? Or is it also possible that you're just too limited? Your capacity hit the limit. Okay, so it's just you suck instead of the result is wrong. Given that idea, there is another conclusion you can say, that is inconclusive. A hidden thing to that is try something else. Okay, which one is more reasonable here? Think about it. You try to show it with the alternating series test, and you couldn't. Okay, should you just say, okay, because I couldn't do that, therefore it's divergent? If you say that, you're basically saying the alternating series test is the uniform golden rule. Okay, if it's not satisfied, you don't have other options. Okay, clearly this is not a reasonable approach. A second thing should say, hey, I tried to use the alternating series test, it failed. Now let me try something else. Okay, and if you really want to say something's divergent, I probably need to try some test to say, yes, it is divergent firmly, instead of saying, no, yes, it is divergent simply because I cannot show it's convergent. Okay, so a reasonable approach is to try to say inconclusive, which means we should try something else. In general, it is difficult, but for this one, it's doable. Go back and think about what you have. Can I do this one with the integral test? No, because it's not positive. It's alternating, remember? Can you do this one with comparison? Same reason. You cannot because you need positive. So once you have positive, the first two tests automatically fail. Okay. Do you have a third thing so far? Which is from 11.2. The first time we did it. Hopefully you can recall, it's called the test of divergence. What it says is, if you take a sequence or series, okay, you try to look at the last term. If it's 0, nothing you can say, but if it's not 0, automatically you can say it's divergent, because basically you're just adding something which is not 0 forever. It's gonna be divergent. Okay? Now let's look at what happens when n goes to infinity for this term here. Okay. Number 1, this is going to be very close to 1. Number 2, this is going to keep alternating. So basically, when n is large, you're just doing almost 1 minus 1 plus 1 minus 1 plus 1 minus 1. And clearly, this one is divergent due to the test of divergence. Okay, so for this case, even though the alternating series test fail, you do not have to give up. Number 1, you cannot say it's convergent. Because it fails, it's divergent. You cannot say that. Number 2, you can try something else. In this case, test of divergence worked. Okay, so I'm going to put a line here and indicate everything above is the formal solution. In the exam, you don't have to show anything below. Okay, you really don't have to. This is just for exercise to show you what happens if it fails. But in the exam, you don't have to write down anything below this red line. Okay, so the alternating series, we have defined it. We have learned a way to actually try to show if it's convergent or divergent. We cannot show it's divergent. We can only show it's convergent. We basically check, are you decreasing? And is the limit 0? Sounds good. Now, what do we want to do next? Let's think about it. In order to know this, let's go over the proof a little bit, okay, about the test of divergence. I will give you the rough idea. The formal proof is actually written in the notes. Okay, you can see from all the way from here. It's fairly long. Okay. So you can read it yourself and try to get it. For now, I just want to lead you through the process. Okay. Let's see what's going on. So, recall, we have an equals this. Okay. We do have another case, which is -1 to the n, but the ideas will be similar. You just throw away the first term, they become similar. So I will just, for simplicity, focus on this one. This means your series is going to be sum which is b1 minus b2 plus b3 minus b4. So plus minus, and all these b's are positive. And you do know bn is decreasing, and you do know limit n goes to infinity bn is 0. With everything I just wrote down, I want to go ahead and try to prove, okay, if we have all this, then the sum of an, we want this, is convergent. Let's see how we do that. Okay, to show the proof, I want to first define the finite sum. And I particularly are interested in even sum. So S to n. What it means is I define a sequence of sum, which is called S2, which is b1 minus b2, S4, which is b1 minus b2 plus b3 minus b4, and S6 with 6 terms, and so on. So from here you can see I'm not taking the random sum here for any number. I'm summing only even numbers of terms together. Okay, I will have S8. I will have dot dot dot. I will have S100. S102, but there's no odd sums. If that is good, you can see all these numbers here keep going defines a sequence. Try to recall what we did in 11.2. All series is nothing but a sequence, because you just let n goes to infinity, nothing become your sum. Okay. Now, if we have a sequence, let's see what we can do with this. Number one, I want you to think about which one is bigger, S2 or S4. What's the difference? Well, S2 is B1 minus B2. S4 is B1 minus B2. Up to now, S2 and S4 are the same. Plus B3 and B4. This term will determine which one is bigger, because if this term here is positive, that means S4 is bigger than S2 because it's basically S2 plus another positive number. If this one is negative, then basically what you are trying to say is S4 is S2 plus another negative number, which make it smaller. So, do you know if this one is positive or negative? It is a matter of B3 and B4, which one is bigger. Now, recall the fact we just wrote down. Bn is decreasing. If it's decreasing, B3 is definitely bigger than B4. Alright? That means this term is definitely positive. That means S4 is S2 plus a positive number is definitely bigger than this. Sounds good? That's the first one. Okay. Now use the same idea. I'm going to ask you a question. Which one is bigger, S4 or S6? Now you can see, with the same analogy, we should focus on this term. B5 is bigger than B6 because Bn are decreasing, right? Then this is positive. Okay. That means S6 is nothing but S4 plus a positive number. That means this is happening. What about S8? I think you can see the analogy now. It's S6 plus 2 more. And this is positive. Therefore, it's bigger than S6. So S4 is bigger than S2. S6 is bigger than S4. S8 is bigger than S6. We can use the same analogy to show S10, S12, just keep getting bigger. It's this sequence here. I'm going to write it down. It's increasing. It's a sequence. It's increasing. And we want to show this sequence is convergent, because if it converges, the series, the even sums will basically be convergent. That's exactly what we want, right? We want the sum to be convergent. Okay, so you have a sequence. It's increasing. To show it's convergent, you just need one more thing. Do you recall what that thing is? Okay, this is called the monotonic convergence theorem. Right? You just need to show S2n is less or equal than a number. Remember, you keep going up. Okay, then it's possible you become infinity, right? But then I put a bar here and say, hey, but you could never go across this bar. Then you have to converge. That's basically what monotonic convergence theorem tells you. So here, we just need this. We need to find an m. Okay, such that all these sums will be less or equal than that. Can we do it? Let's think about it. What's going on here? Let me rewrite this. Okay. Here is S2. Remember, all the b's are positive, right? The negative 1 to the power takes care of the sign. So this is definitely less than b1, for sure, because you are b1 minus something. What about S4? Oh. S4 is this. And what I would do is I would group these two together and give you this with a simple algebra. What is this? Well, same analogy. Is this one positive or negative? B2 is bigger than B3, positive. So S4 is nothing but B1 minus a positive number minus another positive number. It's going to be less than B1. Makes sense, right? Okay. What about S6? S6 is B1 minus B2 plus B3 minus B4 plus B5 minus B6. Again, group this together, group these together. It's going to be B1 minus B2 minus B3 minus B4 minus B5 minus B6. By algebra, you put a negative here, just flip both signs. Same trick, positive, positive, positive. B1 minus 3 positive numbers is going to be less than B1. So through a smart grouping, we can actually show S8, S10, S2, and all the even sums will be all less or equal than B1. Then it's all set. It's increasing. It's less or equal than a number. Therefore, it's convergent, according to the monotonic convergence theorem. So we just prove it. The series is going to be convergent. Okay, I just activated by my series from my iPhone. Okay, so the series is convergent. The proof is basically done. Okay, a key here is by grouping them smartly and use the fact that Bn is decreasing, we can argue that the whole thing is convergent. Now, think about it. There's a gap. There's a hole in our proof. What is that? Well, we did even sum. It may be a dumb question to ask, but what happens to odd sum? Or a more careful way to say it is, does it matter if we just take the regular sum or we only take the sum 2 terms at a time? Let me write down what I mean. When we do things like that, right? When you say you take even sum, you basically are saying, I want to group things together. I want to do these two, and these two. And then I need to ask yourself a question. That is, does grouping change the answer? Can you just group whatever way you want to group them without changing the answer? Go back to the examples we had before. Do you remember this? We had in class, right? We'll ask, okay, what's the answer? The first answer is 1 minus 1 plus 1 minus 1 plus 1 minus 1. This is nothing but 0 plus 0 plus 0 plus 0, right? Together, you have 0. Then we get some guy, I don't quite remember, but saying, hey, what if you group these two together? Then this becomes 1 plus 0 plus 0 plus 0 plus 0, which eventually equals 1. From here you can see you cannot simply just group things according to what you want. You have to be really careful to show that no matter how you group it, the answers are the same. That's why I say there is a hole in what we have here. Another hint is, during all the proof, we never used this condition. Okay, so that's another indicator. Probably there's a hole in your proof. Otherwise, the theorem is wrong. You only need one condition. Why do you need two? Because one condition is sufficient enough. Okay, with that in our mind, I just want to put a disclaimer here in the formal notes. Hey, what's going on here? Okay, I basically copied everything formally, but I did say, hey, note this only proves the even sum converges. Pay attention to this paragraph. To show a general sum converge, you need to actually use the fact. Okay, we skip that part because we just need a rough idea. And also, it's really not clean to show with all the mathematical languages so far because nobody has taken a proof class. But just to give you an idea, it's actually not too hard to think about because let's say if you take the sum, the even sum, to S a million. How do you show S a million plus 1, which is 1,000,001, which is the odd sum, will also be convergent? Well, notice, these two are basically the same, except for one term, that is B, this. right? Remember, this one sum everything up to here. Okay, this one sum to everything all the way up to here. If that is the case, this will be the difference between these two sums. But remember what we said? When n is big, this one is almost 0. So this thing here will be not much different from here, because basically the difference is nothing but 0 if n is huge. That's why even sum and odd sum may go to the same answer. Okay, but that's not too careful. You need careful argument from mathematics, and we don't have the tools introduced yet. So I would say I will stop here, but I think you got the idea. Sounds good? Okay, here's another way for you to think about it, which is kind of fun. Let's go back to the first part. Erase everything here. Okay. Now let's think about how do you prove this one. Use the same idea. Do you notice this is actually what you did? Okay. Let's take one, B1. Okay. Let's take B2, B3, B4, B5, and B6. Number one, you notice this is alternating, right? Positive, negative, positive, negative, positive, negative. Number two, because of our assumption, we said Bn is decreasing. Therefore, this thing will be shorter than B1. This thing will be shorter than B3, B2, and keep going. So you can see the lines become shorter and shorter and shorter and shorter. Good so far? Okay. Now with that in mind, when you try to say, I want to do the even sum, basically what you're trying to say is, I want to put these two terms together. I want to sum these two terms together. I want to sum these two terms together. Okay? So what do you mean by B1 minus B2? That is going to be, if I take B2, put it here. Okay, this will be B1 minus B2. All right, that's the difference between these two, because one is positive, one is negative, they cancel each other. So the first one you have here, B1 minus B2, will be this. Okay. What about B3 and B4? Simply do the same thing, and you will find, okay, this is going to be your B3 minus B4. And this is going to be B6 minus B5 minus B6. Good so far? Okay. Now what you want to do is you want to sum all these small bars together. Each bar comes from two terms before. They canceled, so you have some left over. You put it here. Now what I'm claiming is this sum will keep increasing, or equivalently I'm saying all these bars will be above the axis. All these bars will be positive. It will never be below. This never happened. Okay. Now why is that? Think about it. That is because we assumed B1 is bigger than B2. We assumed that B3 is bigger than B4. We assumed B5 is bigger than B6. So this positive bar here will be always be longer than this negative bar. So no matter what, your leftover will be above. Okay. And then if you sum them together, of course you keep getting bigger because every single term is positive. That's basically what we said here with algebra. Sounds good? Okay. Now what happens to the second case? B1, B4, B5, B6. Okay? 2, 3, 4, 5, 6. For this time, what we did is actually, instead of doing, I probably still need to write it down, B2, B3, B4, B5, B6. Okay. Oh, not B5 here. B5 here. We say, hey, instead of grouping B1 and B2 together, I want to group these two together. I want to group these two together. I want to group B6 and B7 together. I didn't draw. But then, what you have from here is B1. What you have from here is going to be B2. minus B3. What is that? That is going to be putting this bar here and this bar here together. And remember, this bar is longer. So you will have some left over here if you put these two terms together. You have some bar here if you put B4 and B minus B5 together. If you have things here, because the bar keeps getting shorter, every single thing here, because you start with a negative, right, will be always below. Now if you take the sum of all these terms, we're going to say it's less than B1, which is very clear because you start with B1, you minus it, something, you minus something, you minus something, you minus something, you keep minusing things. Of course it's less than B1. So that's actually how we did the proof using a graph, which is basically the same idea. Okay, that's all we have for convergence. Finally, the last thing we want to talk about is going to be the error estimate. Rn equals this, less or equal than Bn plus 1. So let's illustrate with an example. Okay. Let's say number 4. We did this in number 1. Okay. And we say, well, this one is convergent. Now what we want to do is, we want to guess what's the value. Yeah, I know it's finite. Is it 3? Is it 15? Is it negative 2? Okay, can you give me an estimate of the number? And this is what we're going to do. We're going to take out Wolfram. We're going to sum the 100 terms. For example, a computer can do that. We end up with a number. You can type it in Wolfram by yourself. It's 0.68 something. Okay. Then we're going to say this one is an approximation. Of this. It's not this because we only took 100 terms. To finish this, you should take infinite many terms. Okay? But we're going to say, well, I'm just going to use this. Okay? Then what you want to tell people is, okay, this is not accurate, but can you tell me how accurate it is, or what's the precision, or in another word, what's the error? Okay? That is called error estimate. If I'm not happy with error, I'm going to actually take more terms. I'm going to take 1,000,000 terms, use the computer to compute it, and say, okay, I did more terms. Now, what's my error? You keep doing this until you are happy with the error you have. Okay? Now, let's take a look. This is what the theorem tells you. If you have an alternating series, the error is going to be less or equal than Bn plus 1. The error, in this case, are 100, which means you take S 100. Okay, let's say that is A1 plus A2. Dot, 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 plus A 100. You say, hey, this is my approximation of the whole thing. Then what you throw away is A101 plus A102, dot, 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 to infinity. This will be your error. We name it Rn, which is called the remainder, if you try to recall. And then R100 will be all the terms here. And according to the theorem, the absolute value is less or equal than Bn plus 1. Okay. What is n plus 1? That is going to be B101 because your n is 100. That tells you Bn101 is nothing but, remember this is your Bn, is roughly 0.01. Okay. So if you take 100 terms, you got this number, your error estimate will be roughly, actually, let me don't circle this down. Let me circle this down. Will be this, which is roughly 0.01. That means, yes, you're off from the real number, but the real number will be roughly 0.698 or roughly 0.678. Okay, no beyond, no before. So that is a pretty good estimate. And if you're not happy, let's do 1,000,000 terms. then R a million is going to less or equal than B 100,001, which is 1 over, which is roughly like 0.0000123456001. So of course, taking 1 million terms, you have a better precision. Now you're pretty sure it's going to be 688. And with all the decimals, probably the 6th decimal is going to change a little bit, but I think you're safe with 5 digits. Okay. So that is pretty nice for error estimate. Okay, that's how we apply it. Try some examples. But why does the error estimate work that way? I won't go over the proof. You do it by yourself. But let's just look at this graph here. Okay, you're basically saying S2n is less or equal than B1. Right. That means what? That means you sum everybody together here. All together will be just less or equal than the first term. Now imagine the same graph, but this time you don't start from B1. You start from Bn plus 1. Okay, and do exactly the same trick by grouping things together. You are going to have everybody from here to here is going to be nothing but Bn plus 1 plus something like this. If you group two terms together and putting together, use the same idea, then of course this is going to be less or equal than Bn plus 1. Using a similar graph as what we have here. Okay, but I will skip the proof. You prove by yourself. Okay, so that's all we need to say about alternating series. And one thing this time, because I have shot it for 3 times, I forgot something, so I added in the end. That is, why alternating series? Why do we care? Okay, just a quick idea. In which kind of way the nature behave this way? Well, you basically have some number. One is positive, one is negative, one is positive, one is negative, one is positive, one is negative. Okay. If you connect all of them, what do you see? Clearly it's an oscillation. Okay. Even if I have an oscillation here, you shift everything down, even though everything is positive right before you shift. But once you shift everything, it's still positive, negative, positive, negative, positive, negative, positive, negative. So basically what you're trying to deal with is actually oscillation. Okay, so if you have oscillation, what phenomena in nature behave like this? You can simply think about a spring. Let's call this relaxed state. 0, there's no force. And then you pull it to here. You start to release. Now imagine what's going to happen. This one is going to shake all the way up to here. And then this one is going to shake back all the way up to here. You just keep going like this. Do you see an alternating series? If you say this is positive, this is negative, and clearly this is 0 in terms of positions, it becomes an oscillating series. Okay? Or if you think about this, a pendulum, if you release it, nothing is going to start to shake. When nothing swings back and forth and back and forth and back and forth, and if you put a detector only at here and here to record positive, negative, of course you have alternating series again. Okay, so now why do you care about the sum? It's very simple. If you think about it, if you don't think there's any friction, the whole thing is actually really smooth, right? This one just keeps shaking forever. But if there's a friction, you go all the way from the right to the left, but the length here will be less than the length of here because you lose some energy. So instead of shaking forever, you're going to shake smaller, and 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 smaller, because you lose energy. So to tell the difference between these two cases, you can simply take the sum of all these alternating series, and you can prove in this case it's going to be finite. In another word, convergent. That means if you sum all the paths together, eventually you lose energy. Your mass stops somewhere. It stops shaking. But if you sum all these together, you have divergent. infinity. That means what? That means you keep shaking, keep shaking, keep shaking, keep shaking, keep shaking, keep shaking, and that thing that never stop anywhere. That will give you trouble. Okay, but if you imagine an ideal case, everything is super smooth, there is no friction. Maybe by conservation of energy, you never lose any energy. You probably is going to shake forever. So alternating series is closely connected to oscillation. And if it's convergent or divergent, really gives you an idea of, for example, if there is an energy loss or not. But there is so much more you can tell, because the things oscillating can be energy, can be phase, can be path, can be positions, can be all velocities, all kinds of things. Okay, that's why we care about it. Okay, I think that's all for today. I'm really tired. This is the third time I'm doing it, and hopefully I didn't forget anything. Okay.